we're now going to consider the opposite of differentiation, which is integration. In many ways, integration is a much more stable operation because differentiation itself, if you have noisy data, derivative estimates are exceptionally difficult to produce because the slope can be highly volatile depending upon how noise is influencing the data points. Whereas integration is a smoothing operation, you adding things, so it's much more robust to noise in the system. In either case, integration and differentiation are sort of the two primary things we think about when we work with calculus-based rule sets. And physics engineering is mostly based upon calculus-based models. And this is how we've made so much progress over centuries now in terms of understanding of our physical world, is that science and engineering systems are typically represented as relationship among derivatives, and also integrals play a key role there because it is the anti-differentiation rule that we have available to us, okay? So I want to come to this, and we're going to build this out, obviously in Python, and it's really part of the scientific computing platform because differentiation and integration are the two sort of rock beds for building everything we have in scientific computing. And so let's go ahead and start talking about this numerical integration. So numerical integration now is going to be basically what we learned in calculus. Typically in calculus, the first quarter of calculus, you learn this idea of slope formulas and limiting processes and how to compute that slope and the limit as delta t goes to 0. And integration itself has a very similar structure. And let's talk about what it means to define an integral. So here's what an integration looks like. The integration symbol's here. If I integrate from a to b, a function f of x dx, what we learned in pretty much the very first day of integral calculus or integration schemes is that basically this is representing a sum over as of, let's say, typically we would do little rectangles. As the rectangle width goes to 0, I add up all of these rectangles with the rectangle's width going to 0 in such a way that this actually makes sense. So really, this is a length times width calculation, right? So this is the height of the rectangle, that's the width of the rectangle. And of course, as the width of the rectangle goes to 0, then presumably the area goes to 0. But in such a way, because I'm adding an infinite number of these rectangles, that this actually makes sense. And that was the beauty of calculus. We had this idea of learning how to go to these limiting processes and making sense of them, both in the derivative and in the integral. But just like with differentiation, where scientific computing just simply says we're going to undo calculus, integration does the same thing. I'm not going to go to the limit. What I'm going to do is take a finite set of rectangles of width h and just add them. I'm not going to do this limiting process because the limiting process for the computer is difficult to handle because you either have divide by zeros for derivatives, or here you're multiplying by infinities here because you have an infinite number of rectangles. So we're just going to take a small finite width rectangle and add them together. And of course, just like Taylor series expansions, our error is going to be dominated by how thick that rectangle actually is. So let me give you a pictorial of this. This is sort of your canonical picture of what we do with numerical integration and numerical integration schemes. I just add up all these rectangles under this curve all the way across, and the sum of that area of these rectangles is the area under this curve altogether. What calculus does, or what it forces us to do, is to make sense of the fact that when these rectangles shrink to width 0, and I have an infinite number of them, that I actually get a finite value that represents the area of the curve. And now we're not going to do that anymore. We're just going to say, pick the width of this, do the integration. Okay? So it's much simpler in many ways. All right, so that's numerical integration. That's going to be about as simple as it is. We're going to tell our computer to go sum a bunch of things. If one thing there's a computer is good at, it's adding, subtracting, multiplying, and dividing. And it never complains. It just does it at any scale we want. So we're going to tell it, go do this for me, and it's going to compute for us integrals as we wish. Okay, so now we're going to come to this idea of what's called a quadrature rule. So it's basically the same concept that was in that picture, which is I'm going to add up a bunch of things, a bunch of rectangles. It doesn't have to be rectangles. It could be different structures, but you want finite width. It could be a rectangle with a flat top. It could use the left point, the right point. It could be a trapezoid instead that goes between the 2 points. There's different options about what we do here. And so the quadrature rule is a very, very generic representation. What it says is, with weight wk, I add f of x at x of k. So I have a finite number of points. Remember, this is a finite difference scheme. So when I take a domain, I'm going to chop it up into a certain number of points. And once I chop that up, I've explicitly picked then a width of what I have there of the cells, and also I've fixed the number of points. So f is the function I'm trying to integrate underneath, evaluate at each one of these points I've chopped it into with a weight wk. And of course, this is a very generic representation. And again, just expanding this out. So I'm going to add all of these up to get an estimate for the integral. The real question comes, what are the weights I should be using? That's the biggest thing we have to define here. What is it, W0, W1, all the way to W of n? And there's a lot of different architectures for getting this, depending upon what kind of accuracy you want in your solution. Just like when we were doing finite differences, where we could use 2 neighbors to estimate the derivative with delta t squared, 4 neighbors to get it to delta t to the 4th, 6 neighbors, delta t to the 6th. That in the same way, we're going to use that kind of idea of what kind of accuracy I want to determine what these w's should be in order to compute the integral to some prescribed accuracy. But in general, it's called a quadrature rule, and we're going to have an error. So even after I approximate this derivative by this quadrature rule, the fact is there's an error, right? So however I approximate this, I have certain accuracy, and I've made an error. In the Taylor series expansion that we did for differentiation, that error came from a truncation of the Taylor series. And it's going to be the same here. We can actually estimate this error through truncation of the Taylor series, okay? So let's go and actually estimate some of these simple formulas or simple quadrature rules. The easiest one is called the trapezoid rule. Here's the trapezoid rule. If I'm going to integrate, and here's my little cell going from x0 to x1, f of x dx, what I can do to estimate the right rectangle I want to add to this is it could just simply be the average of f0 and f1. So I'm integrating over a cell, and I say, well, what is the height of that cell? It's the average between the left point and the right point. So that's what the average is. You take one point, take the other, divide by 2, that's the average, times its width. This is length times height. Okay? Sorry, width times height. The width is h. The height is the average of the 2 points. Okay? Now when you do this, you can actually show by doing just a Taylor series expansion, just like we did before, that the error here now has an h cubed over 12 second derivative. So notice this is h cubed there, that's h there. So another way to think about it, this is h squared smaller than this. And as I make h small then, that term, if I cut the h in half, that term drops by a factor of 4. Okay, so I can push the error down by taking the h smaller. So that's called trapezoidal rule, and you can play this game, and again, it's purely based upon Taylor series expansions to do a better and better job of producing an integral estimate. So let's start here. Here's some others that you might do. Simpson's rule. Let's talk about Simpson's rule. This is a very commonly used one. Simpson's rule now goes from x0 to x2. So it's actually looking at over 2 cells, so x0, x1, x2. And what it does is it approximates a parabola between f0, f1, f2. So it fits a quadratic there, and So here's the estimate for this. It's h over 3, f naught, 4f1, f2, but here's the big deal. This is, again, basically estimating the same integral, but now instead of there being an h cubed there's an h5. Just like when I did finite differences, the more neighbors I use, I could push the error down. I use more points, I push the error down. Okay? That's the common thing across all of these Taylor series-based methods, is I can push the error down. Here's a Simpson's 3/8 rule, slightly different formula, but notice now I'm using 4 points, h5 is the error. In Boole's rule, I can push it all the way down to h to the 7 by using more points here. So you can see there's all kinds of schemes you could come up with to estimate the derivative based upon, first of all, ease of implementation, your error estimate requirements. You may need to get error below a certain level, but these are all formulas that can be really easy implemented in Python in a for loop, okay? So keep these in mind, keep these handy somewhere. These integration schemes are quite useful and used all the time across science and engineering, because that's actually all we do, is we compute derivatives, compute integrals most of the time. Okay, so let's actually look at this from a graphical perspective, by the way, these different schemes we were looking at. So trapezoidal rule is just this. So I have some curve here with a set of points. The trapezoidal rule just simply says compute the area of this here, which is basically, this is, you know, using one point, the other point, it's essentially taking the average height of that to compute the area of that rectangle. And then I just do it across the entire domain that I would have to integrate under. Simpson's rule fits a parabola to the points. So that's what you're looking at here. And so now it estimates two of these delta x's, or two of these width boxes, jointly together, and that's called Simpson's rule. And I've pushed the error down by using that down to h over 4. This is the Simpson's 3/8 rule. Simpson's 3/8 rule actually uses 3 widths that you would do to compute the area in the curve. And then this is the Boole's rule, which gives me all the way down to h to the 7. And the way I get the error so far down is I use, now look at this, 4 cells to actually get a computation for the derivative. The real advantage here too, by the way, is when I add these together, I have the estimate for that entire place, and now I just do the next 4 and the next 4, versus if I use the trapezoidal rule, I compute this, now I have to compute the next cell, and walk that thing across, okay? So these are just schemes that are commonly used. Simpson's rule is probably one of the more widely used. A lot of people know Simpson's rule, and because for just a little bit of extra cost, you improve the accuracy quite a bit. Boole's rule, do you really need h to the 7th accurate? You may, but oftentimes Simpson's rule is good enough for doing the estimates that you might need in practice. Okay, so let's talk about the computation, by the way. And now, so each one of those was giving you a rule for how to estimate the area under a cell or a couple cells. But really often we want to integrate across an entire function, and we can start using what are called composite rules. Composite rules are ways to essentially make the computation faster. And you'll see the composite rule highlights to us that there's actually structure in this computation. We can take advantage so that we don't have to do repeat computations that we would have to otherwise. So here, for instance, is a trapezoidal rule that you're going to use, a quadrature trapezoidal rule across the domain, which is basically, remember, the average height of each cell times its width. That's it. So you just add up all these triangles. But let's expand this out and actually look at the structure of it. So if we expand it out, here's the area of the first cell, h over 2 f naught plus f1. The second cell, h over 2 f1 plus f2. Third cell, fourth cell, and so forth. Notice here that f1 shows up here and here. And I'd have an f2 here and in the next cell. So I'm essentially, if I do this directly the way it's here, I'm having to double calculate the contribution of f1 first with h over 2, then with h over 2. But since I already know they're both contributing, let's actually bring them together into the composite rule, which is h over 2, f naught, there's the 2f1, the 2f2, and so forth. So this thing here is essentially twice as fast to compute because I've already taken account all the redundant calculations I would have to do otherwise. And it leads us to this improved formula, which, often computers today are so fast you don't care. But if you were doing this at scale, this is basically twice the speed. So certainly when these algorithms were invented, we had much, much slower computers, right? And so if computations took quite a while. Today, computers just, they fly along. We don't often have to think about this. But again, if you go to large scale computing, you should start taking advantage of such schemes in your problem. Let's code it. Before, what we did is we wrote some Python code for doing numerical differentiation. Here's some code for doing numerical integration. Again, I'm going to go ahead and break up a domain that is of a certain size. So here's the h, right? So I'm giving you the width of each cell. Then I can compute a range, and I'm going to integrate over cosine. And of course, if you integrate over cosine, inverse differentiation is sine. So the exact answer is sine. So when I integrate this, I should get sine back out. And so what this code does is it allows us to build a model, play around with the h, and see how well we did because we actually know what the answer is. The answer is sine. So let's go ahead and do this. So I'm going to keep track of the total area. Here it is. And all you're going to do here, first, this here is the simplest model possible, which is the trapezoidal rule. Point in front, point behind, you take this average times the height, add it together. So that's in the total area. So that's the trapezoidal rule. It's as simple as that. You just write a code to walk across the domain, add up the area of each triangle. We can keep track of the total area here as we march along. So you're basically computing the cumulative area under the curve. And you can plot this, okay? And you know that the answer is going to be a sine. So later you can plot that and see how it works. And this is accurate to whatever this h squared is, okay? If we decide to use trapezoidal rule, you do it here. Now notice in the trapezoidal rule, I'm doing 2 cells at a time. So first of all, my loop, instead of going a certain number of points, I'm only going to go half that because I'm doing the area in the curve 2 cells at a time. And here's the formula. This is the formula that we have for the trapezoidal rule. It's directly out of the table that I showed to you. So you're using 3 points, okay? And this is fitting a parabola through them. Use those 3 points times the width, h, and this gives you then, through Simpson's rule, it gives you an h to the 4th accurate representation of what is going to be the sine. So you can see these are very simple, okay? And a lot of numerical integration schemes are actually built in directly into things like Python, but these are so simple to write that you could use those or just use these here, okay? So that's how you would actually code these things in practice. And so that's one way to do this. Now I want to talk about some improvements a little bit around this idea of accuracy. Remember, a lot of scientific computing is about not just writing code, but it's about how quickly can I solve a problem? So in other words, computational speed really matters. And how accurately can I solve it? The overall objective in scientific computing is to solve something as fast as possible and as accurately as possible. Okay? So even in these 2 code blocks, this is really getting to the issue of much higher accuracy than here. And now let's address the speed issue. Remember, even the composite rule I showed you was all about speed. But let's go ahead and deal with speed as well. So here's what a recursive refinement rule looks like. So suppose you actually pick an h to start with, and you actually solve this and you compute through a trapezoidal rule the quadrature that you want, okay? But suppose it's not accurate enough. And so, okay, I want to refine my calculation. But the question is, do I have to do all the work I just did over again? And the answer is no. So the idea behind the recursive refinement here is if you actually look at the formula for this and you expand it out, here's what this thing might look like here. And what you could say is, okay, I have a representation of the solution with a certain, say, in this case, it's the width of this is 2 delta x. And suppose I want to refine it now to get a more accurate representation by making the width of these cells smaller. Well, all these terms show up whether it's 2 delta x or x as the width of your cells that you're using. So what you could say is there's a previous calculation, you can use it, and you can say, look, if I want to compute the quadrature using h, I can use this previously computed, which used 2h, and simply add the terms that I'm missing, which now gives me the improvement of refinement, which gives me terms in between those that I had before. So notice this is a recycled computation. And since we love doing recycling here in Seattle, you'd always want to use something like this, right? So it's like, I don't have to do the work again. I've already got one computation. All I have to do is figure out, and it's at 2 delta x, all I have to do is take the points I missed in between, add those to what I already had to get the computation here. So again, saving you a factor of nearly 2, right? So this is like twice as fast. So between your composite rules, which make it twice as fast, or this recursive refinement, which is twice as fast, now you've speeded this thing up potentially up to a factor of 4. So these are the kind of things you think about in scientific computing. Remember, computers used to be quite a bit slower, so thinking about this was really important because compute took quite a lot of time. A lot of times for simple problems, you never have to think about this because you just rerun it because our computers are so fast. But again, when you go to scale, big problems, you might want to start thinking about these things. So that kind of finishes the things we want to talk about with numerical integration. Numerical integration, the nice thing about it is typically it's a much more stable algorithm to implement or to compute than numerical differentiation. Numerical differentiation is something you have to really watch out for. Numerical integration is, if you can do the differentiation, you'll be fine with the integration. It's a much more stable algorithm. It's a smoothing algorithm, whereas numerical differentiation, especially with noisy data, that noise can really affect your derivative estimates. And doing numerical differentiation of noisy data is in itself a lot of work, and a lot of different techniques have been proposed to take care of that. We'll consider those in later lectures.